So this module here, it's going to talk a little bit more about the operation of a transformer and what's going on as we go from no load to full load. So when we're looking at a transformer, so on this transformer, obviously it's got a primary winding and it's wrapped around a common core, and it's got a secondary winding wrapped around that same common core. And when we're looking at it, because this is just a coil of wire, it's going to have resistance in it. So this little diagram here is in your ILM, and it's just an equivalent resistance of what's actually in the winding here. And because it is a coil of wire, it's going to have reactance as well, so inductive reactance. So both of these, primary and secondary, because they are coils of wire, are going to contain resistance and inductive reactance. And we to begin with, and we'll kind of come back to this here. So just understanding that both of them have resistance and inductive reactance in both the windings. So a transformer at no load conditions is what we're going to look at first. What does that mean? That means I'm going to apply rated voltage here. Let's say I have a 240 volt transformer and I don't have anything on the secondary at all. So let's say it's a 2 to 1, so down to 120, let's say. So I'm going to apply 240, the turns ratio, say it's 2 to 1. It's going to give us number of turns. For every 2 turns on the primary, there's 1 turn on the secondary, and it's going to make 120 volts on the secondary, and that will be our open circuit voltage. Okay, so if I put a voltmeter here, I'll read that 120 volts. Now, what's happening during no load conditions? So this is kind of the preamble from when we go to load conditions, understanding what's going on. So if I put my applied voltage on here again, so 240 volts, what we would see is we'd see a little bit of current flowing through this primary, all right? And it is just a chunk of wire. Why isn't it a really, really high current? Well, it's a coil, right? And it has an iron core, and it's going to create counter EMF in that coil, which opposes our primary voltage. And so we end up just getting a little bit of current flow through that. We call that the exciting current. So if I put an amp meter on right here, okay, it's going to read a little bit of current flow. Let's say it's going to be about a half an amp in this one, okay, 0.5 of an amp, and we call that the exciting current. And what that exciting current is enough current to establish the magnetic field, okay, which travels through the core. And so that exciting current has 2 effects. One, it creates the counter EMF on the primary, and it induces the voltage on the secondary. And so we would see our 120 volts here. So that's what our exciting current would be doing, creating our exciting flux, responsible for that counter EMF, as well as inducing our voltage on the secondary. So here's a little, I think you call it GIF. I made this. Here's an AC supply, and as we have a sine wave here, so this is basically the current. I got it here. I just don't want to draw on that. So it goes up, comes down to 0, and then changes direction, goes to a maximum in the negative direction, back to 0. So as current flows through this circuit, we would see that it increases intensity, and with that increase in intensity, the magnetic field will get stronger and expand. So that expanding magnetic field is what cuts across, well, itself right here, as well as it cuts across the secondary. And so when it cuts across the primary winding right here, it creates that counter EMF. When it cuts across the secondary, it induces the secondary voltage. So for the top half of the cycle, this part right here, okay, it's going to create the magnetic field in one direction, and then when the current changes direction, it's going to create the magnetic field in the other direction. So as we see here, transformer has no moving parts. The secondary here is getting its induced voltage from a moving magnetic field, but it's due to the current changing its intensity. It's getting higher, lower, then changing direction. So transformers are strictly AC machines, so they only work with AC supply. Okay, so transformer action operating with a load. So this is where things change a little bit. Same transformer, so we got, 240 volt here. Let's go down to 120. Okay, so we have that exciting current flowing through. It induces a voltage at primary and secondary, creates our secondary voltage. Now we put a load on. So now that we put a load on, current is going to flow through the load. So we have current draw through the secondary and returning. So with that direction for the first half of the cycle, let's say, then changes direction for the second half, goes the other way. All right. So now things change a little bit. When I put load on this and current draws, every time we have current flow, it's going to create a magnetic field. So this secondary coil right here, as current flows through it, it creates a magnetic field. And so if we look here, this is an illustration right here, this little line here of the secondary current flux. So it creates a current flux. Every time you have current flow, it's going to produce a magnetic field. So at this point in time, let's have a look. This is due to Lenz's law, just like it was on the primary. The induced voltage is always a way that opposes the voltage that caused it. So we have that same thing happen on the secondary. As we pull current off here, the direction of the magnetic field produced by it is going to be an opposition magnetic field that produced it. So you see that we're in opposition at that moment in time if we were to look at this. So the secondary flux will be exactly opposite the direction the exciting flux is. Well, what happens if we have two fluxes going opposite direction? They tend to cancel each other out. So the overall magnetic field would become weaker. So we'd have less flux density. Okay, so how does that affect the primary here? If I drop the overall flux going through the core, will I have as much counter EMF or self-induced voltage on that coil? I won't. It will not induce as much counter EMF on that coil. So if the counter EMF is what opposed the current going through in the first place, and we drop that counter EMF, what's going to happen to the current on the primary? The I of the primary will then increase. It's going to go up because there's not as much opposition to current flow on that primary circuit anymore. And so makes sense. When I put load on the secondary of a transformer, what's happening magnetically is going to make sure that the current comes up on the primary as well. And so now that I have that primary current flow, it's not just the exciting current. We now actually have a primary current there. It's going to rise, and what's going to happen is it's going to rise until it's equal and opposite to that secondary current flux. So it's always going to match it. So it'll rise till it gets to that level. So essentially, it rises till it cancels out that secondary current flux. And what are we left with in the core? Our original exciting flux. That's it. Okay. So the primary current rises until the two fluxes basically cancel each other out. So it's a bit of a balancing act. So if I were to take load off of the secondary, so let's say that I somehow could adjust this load and I was at 10 amps and I dropped down to 5 amps. Okay, if I drop down to 5 amps, the secondary current flux would go down. And so what would happen is that we would get a little more counter EMF now, and the primary current would drop down, dropping down the primary current flux. So it's really just a balancing act between the two, and it's about that magnetic field and what's going on with that magnetic field. All right, so now that brings us to voltage regulation of a transformer. I do have one example of a calculation here. So if you recall back in first period, you guys learned about batteries and you guys put them under load. So we did an open circuit voltage of a battery. It was like 13.2 volts, like on a 12-volt battery. Let's say we had a car battery. And then we put it under load, and as we put it under more load, we'd see that the terminal voltage would change as we put it under load. And that was due to internal resistance within that battery. So it would have an internal volt drop. Well, transformer is no different. When I go and I put this under load, let's say that if it was open circuit, that same transformer, 240 down to 120, open circuit, I get the full 120, somewhere around there. But as I put this under load, current begins to flow through the windings. And so because it has internal oppositions, it's going to have an internal volt drop. Okay, so now not every transformer is the same. The different transformers, based off their quality or how they're built, they have what we would call really good voltage regulation. So their voltage regulation voltage regulation is basically the percentage of percent regulation of a transformer is the percentage change of secondary voltage from no load to full load. I'm going to put the formula up here, and I need you guys to really have a good look at this formula. Because you're going to be asked to calculate percent voltage regulation of a transformer. It is V no load minus V full load divided by full load, okay? So make sure you get that correct. A lot of people will try to divide it by the no load voltage. It's divided by the full load voltage. So no load minus full load divided by full load. So here's an example using that. So there's our formula. If the secondary no load voltage of a transformer is 600 volts and the full load voltage is 585 volts, what's the percent voltage regulation? V no load, so 600 volts minus 585 volts and divide by full load. Full load is that lower voltage, 585 times 100. Anybody have a percentage?
2.56.
Sounds good. 2.56. Awesome. Right there. Yeah. Okay. We're going to get into a little bit of losses here on the transformer. And the first thing here is we're going to talk about core losses. All right. So when we have core losses are constant from no load to full load. That has no bearing on it. So they're constant when we're talking about core losses. All right. Two of the things that make up core losses, and you guys studied a little bit about iron cores before in previous years, is they have two components to it: eddy currents and hysteresis. So we're talking about core losses on a transformer. So as good as a transformer is, it's a very efficient machine because it has no moving parts. It still does have some losses. Eddy currents are created when we have a moving magnetic field. Because our core is iron itself, it's going to create circulating currents within that core. And so because currents are circulating or voltage is being induced on that core, it creates a little bit of circulating currents within that core. And it can create heat due to the eddy currents of that transformer. So manufacturers here, what they do is they do this with thin laminations. Okay, so really thin laminations going, and then they stick it all together, a little bit of what is it called there, lacquer in between it, so a little bit of insulation through lacquer in between these laminations. And if you look at the side of a core, you're going to see those thin sheets. So that helps to stop the eddy currents from traveling too far and creating too much heat. So that's one of the things they do. Is it perfect? Nope, but it's better than just a solid iron core. The second part they have with this is hysteresis losses. So hysteresis occurs when we have an AC circuit and the magnetic domains are continually flip-flopping because our current is changing direction. The direction of the magnetic field will also be, so at the molecular level, they're going to be, the magnetic domains of the iron are going to be changing direction, north-south, north-south. And this creates basically internal friction as well, and heat. So we have a heat loss due to that too. So those are all our losses. What they do with that is they try to make it with something called silicone steel, okay? And that tends to reduce the effects of hysteresis. So that's just another component of this. So one of the requirements for core losses, it's not about how much current's going through the conductor. What it is about is the rated voltage is applied. So as long as I have full voltage on a transformer, full voltage, I'm going to see the core losses. And so it has no bearing. Load has no bearing for core losses. As soon as it's energized, it's good. That's when you're going to see and has full voltage across it. If I reduce the voltage down, the core losses will go down. But if I increase the voltage and leave it at rated, you're going to see its full core losses. And if I were to put a watt meter on here, I might have another diagram of this. And it's under no load conditions. There's my there's my voltage coil. Right? So there we go. So we've got a watt meter on here, voltage, current. Yeah. So it will read our core losses when we have an open circuit test. That'll be our core losses of our transformer. They are fixed as long as we have rated voltage on there. All right, I'm just going to erase this for a sec. Core is made up of thin laminations, reduce eddy current, silicone steel used to reduce hysteresis losses of a transformer. So one of the ways, like I was saying, that we can do to determine the core losses of a transformer is the open circuit test. So we just put our rated primary voltage on our transformer and we connect up a watt meter, okay, and no load on the secondary, so no load over here. And this needle on our watt meter, providing we got it connected upright, it will move a little bit and it'll show a few watts. Depending on the size of your transformer, could be 5 to 20 watts on our little transformer, somewhere in there. So it's not a whole lot, but it does tell us our core losses. So just remembering that open circuit test used to determine core losses. In your ILM quizzes, it talks about the open circuit test as well, that it applies a certain amount of volts to the H winding, and you get a certain amount of voltage on the X winding. So that will also be your rated voltage of that transformer when you're reading through those quizzes. All right. The wattmeter reads power losses due to the core losses. So very important again, core losses are dependent upon the applied voltage. If constant rated voltage is applied, the core losses remain constant from no load to full load. So the next loss is that copper loss. So remember, of the two losses on the transformer, we had copper and we've got core. Copper losses in a transformer. So that's exactly, so as we talked about it, there is your coil of wire, and it has resistance. Okay, so each one has resistance. All right. So as we pull current through that secondary winding, and the current rises on the primary winding, it's going to create heat losses within that coil itself. So they're copper losses. Let's have a little look. Copper losses occur when current is flowing both the primary and secondary windings. Those windings itself will heat up. I want to pay attention to this formula. It's one of our power formulas, P equals I squared R. So we are going to come back to this. I'm going to do some recordings of sample questions, but the more load that we put on this transformer, the bigger the copper losses. So they are affected by the load. And it is the actual current flowing through the windings, okay? It doesn't matter if it's in phase with voltage on the load or if it's out of phase. This could be an inductor or a capacitor, okay? If it draws 10 amps, that 10 amps is gonna go through that winding. If this is a 2-to-1 transformer, it'd be 5 amps over here. That's what's gonna flow through this winding, okay? And so this transformer doesn't matter if it's in phase or out of phase. That current must travel through this copper wire. And so it will always produce I squared R. So whenever we're looking at a load on a transformer, we need to know the I total of that load. It's total current, when we don't care if it's in phase or out of phase. That's why our transformers are rated in apparent power. The transformer has to be able to handle that current, okay? And we can actually figure out the individual power losses. If we know the current and we know the resistance of each one of these windings, so this could be for the primary, okay, then we can multiply it out and find the actual power losses, CU loss, on the secondary. So it is very much determined by the amount of current flow through this transformer. And same thing over here, we can figure out the I squared R losses of the primary. So we need the I of the primary squared times the resistance of the primary to figure that out. So keep in mind, this is a square function of the current, okay? Because we are going to be utilizing this or talking about what percentage load this transformer is under. And so we have to remember that those losses are always proportional to the square of the current. And later on, we're going to be squaring our percent load when we know full load copper losses. Okay, how can we figure out the full load copper losses on a transformer? Well, we do this thing, it's called the short circuit test. So we would take a variac here. So a variac is an auto transformer. So basically we can dial it up and down and adjust the voltage. So it's a variable voltage supply. We'd put a watt meter on, and so we have our current coil connected and our voltage coil connected. And this is going to read our copper losses in this case. On the secondary side, we put an amp meter and we just short it out through the amp meter. So we'd have to determine the rated, I secondary rated, and then we'll watch our amp meter right here. So let's say that we did a calculation here and our secondary rated current, say it was 10 amps. Okay? I'd be watching this amp meter and I would slowly dial up my variac here, turning it up, very slowly adjusting the voltage on the primary until this amp meter read 10 amps. Okay, so we've called this a short circuit test. Because an amp meter like this, an amp meter has no resistance in it, that is a short circuit. You never put an amp meter across something in parallel. You always have to put it in series with whatever you're trying to measure. And so it's a short circuit through the amp meter. Once I dial up that voltage and I get the full 10 amps here, I would read my watt meter. And this variac is probably going to be sitting at like maybe 5 to 10 volts. That's it. Well, you'd never make it to 240 volts if this was a 2-to-1 transformer here. If this was 240 primary, 120 here, that voltage barely has to go at all to make rated current flow in that secondary. So whatever the watt meter reads, that would be your, and this is going to give you both losses. It combines it. This watt meter reads both. That is your total copper loss right there, or your full load copper loss, total copper loss. Because we're not at rated voltage, it basically very, very little core losses. We're only at 5 volts. For core losses, you needed rated voltage to get to read that. So this test really is good at isolating your copper losses. So it's called the short circuit test. So full load, I should say, copper losses of this transformer. One other thing that we would get from this is something called the impedance of the transformer. I've got more slides, but this voltage here on our variac, if we put a voltmeter across here, whatever that voltage is, it's very minimal. That is what's called our impedance voltage. So that's the minimum required voltage to make rated current flow through a transformer's secondary when it's shorted out. And so we call that the impedance voltage. And we're going to use that to figure out the percent impedance and some other calculations here. Okay, here's a little diagram of that topic here that I'm just talking about. So we have a variable voltage supply here. We have a shorted secondary. Same test. We just removed the watt meter. When you guys come in to do lab here, we're going to do this test all at once. So we're going to measure voltage and the watt meter to see what the copper losses are. The voltage here from our voltmeter is our impedance voltage. And the watt meter reading, had a watt meter in here, is our full load copper losses. Okay, so onto this impedance voltage here. So whatever that, say we're at 10 volts here or something. Okay, so 10 volts. If I read 10 volts and this is a 240 to 120 transformer, okay, we could calculate the percent impedance of this transformer. So the percent impedance, we say it like this, percent IZ or percent Z. It's usually stamped on the nameplate, but we're going to be doing some testing where we can calculate this. So percent IZ is equal to the impedance voltage divided by your rated primary voltage. So V primary rated times it by 100. So in our case here, if we got to 10 volt and we divided by our rated primary of 240 times it by 100, what would be our percent impedance of this transformer? So about 4.167 or 17, close enough, percent. Okay, so that'd be the percent impedance of this. So the percent impedance, it is valuable to us because that can tell us what our rated secondary current flow under short circuit conditions maximum is. So our secondary maximum short circuit current. So calculate how much current can this transformer put out under short circuit conditions. And why is that important? Well, we have to purchase and install overcurrent devices that can safely interrupt that short circuit current. And so, for example, I can have a 15 amp fuse that is rated for 10,000 amps, which is our standard rating, or I can buy a 15 amp fuse that's rated for 200,000 amp interrupting capacity. And I have to adjust that interrupting capacity based off of the transformer that's feeding that branch circuit. So if I were to, say, have a really high secondary short circuit current available, and I only put on a 10,000 kA, so 10,000 amp, so 10 kA, an interrupting capacity fuse, well, it might blow up if I have a really bad short circuit, or in a breaker, it could melt. It may not function properly. They're not rated to interrupt that high of a fault current, right? So the 15 amp rating, that's its continuous rating. So if I put too many lights on, or the motor goes draws too much current, that may trip that fuse at 15 amps as soon as we approach near that. But if I have a really bad fault current, will that overcurrent do its job? Okay, so they have different ratings they are tested at that will successfully do its job and open up the circuit. So it's called interrupting capacity, and that's why it's important that we can determine, using percent impedance and the VA of the transformer, determine its maximum short circuit current. So I'm going to do some calculations on this, some more calculations on impedance voltage, plus I'm going to do quite a bit on efficiency coming up in videos here. What else is in this ILM is paralleling transformers. Okay. So paralleling, this is a simple example of paralleling two single-phase transformers. So in this we have two transformers in parallel, and by doing this we can basically add their kVA up, and we've got a larger transformer now. So instead of having just one large transformer, we can do two transformers, smaller transformers, to get the same kVA that we need. Now, this can be quite hazardous as for us as electricians, and it's because of backfeeding. All right. So if I were to open up this first transformer here, and I didn't have the second one opened up, what would happen is I would think that when I open up this first one, I could go ahead and work on these terminals here on the H side or the X side. But what actually ends up happening is that if I don't open up everything in parallel, we'll get backfeed. So it'll induce the voltage on the secondary here. It'll come back, and we have full voltage on the secondary from this transformer here, and it'll induce a volt on the primary. So everything will still be live. So that's one of the big hazards when you're paralleling transformers. Ensure that you have opened up all disconnects to every one of the transformers in parallel, and it's completely de-energized before you try to do any work on a parallel transformers. So it can be quite hazardous. So make sure that you avoid backfeeding. So we must be able to disconnect the secondary of a parallel transformer as well as the primary. So let's say I didn't want to take the system down. I would need to make sure that I opened up the secondary as well. So we would need to disconnect on the secondary as well. And then you could isolate that one transformer, remove it, and put it back, or whatever you needed to do. So paralleling transformers, a couple of this, 4 requirements. They must have the same no-load secondary voltage. So if we don't have that, it could create unnecessary circulating current between the two and result in transformer heating and possibly reduce kVA transformer burnout. So it'd be like putting a 12-volt battery that's fully charged in parallel when the one that's not charged. You're going to see the fully charged one will discharge to the one that isn't charged, but it's never going to equal out here. So it'll always have that current flowing between the two, creating that heating. If they are tapped, must be on the same percent taps regarding keeping the voltages the same, right? So different tap setting could result in different secondary voltages. Must have the same percent impedance, plus or minus 5%. So that's kind of the the leeway between the two impedances. So the reason why is if they don't have the same same percent impedance or internal opposition, they're not going to share the load equally. One transformer will take more, it's a bigger share of the load than the other one. So even though you got two, let's say 100 kVA transformers in parallel, if one's got a high percent impedance, the other one's got a low, the one with the low percent impedance is going to take a lot greater share of the load. And so it will be loaded up to 100 kVA long before the other one gets even close to 100 kVA. So you might cause lower percent impedance transformer to become overloaded. And the other thing, they must be connected with the same polarity. So you don't want to mix up who's X1 and who's X2 on these. And this definitely a big thing when we get to three-phase transformers. Three-phase transformers are just three single phase transformers connected up in either Y or delta. And if we have the wrong polarity, we're going to have a short circuit and a little bit catastrophic.